I'm going to move us on now to our lightning talks. So we've got now 4 talks of 3 minutes each, and after this we will be heading into breakout rooms. So we will open up the breakout rooms and you can go and ask questions of these 4 speakers, or just find out a little bit more about their work. So I will kick us off with Sam. So Sam, please do go ahead, and if you are sharing or just speaking.
Brilliant, thank you. Let me just share. So hi everyone, thank you. I'm going to be the first lightning talk of the day, which is just a very quick 3-minute update on the project. So I'll try not to ramble on, but just a very quick introduction. I come from NHS Blood and Transplant, and the model I'll be demonstrating today is all around how we can predict the outcome for when our donors book into a blood donation session. This is very much an unfinished model, so I will just be showcasing a demo version today. I'll just get that out there now. The reason why this has become key is that we do place a lot of reliance on our donors to book their own appointments in. They do it out of the good of their own hearts. But there are several reasons why they might not be able to donate on the day that they book in for. So they might cancel their appointment, they might miss or not attend or not be able to get to their appointment on the day, or they may even come in, but for maybe a medical reason, they might not be able to donate. So when one of these things happens, not only do we miss the collection, but there's also an opportunity cost because we might have been able to fill this appointment elsewhere. So in order to sort of try and combat this, I've used a technique called a random forest, which is effectively a collection of decision trees to take into account the characteristics of the donor as well as the specific booking, and to try and get a judgment of whether or not the collection will take place. If yes, then brilliant, we can go ahead as normal. But if not, we might want to take further action and book someone else in for the day. Don't worry, I'm not going to explain the individual model in too much details, and I'll cut straight to the output. So like some of the other examples that we've seen today, the output is showcased in the Streamlit app. So this will give the session managers the option to search for a specific session that they're looking at, see how many bookings are already made for that session, and see how many are likely to actually result in a successful collection. We generally wouldn't expect anywhere near 100% of appointments to be successful, but where there is maybe a significant gap between the number of bookings that are made and the number of predicted collections for that day, this does allow us to take some further action and maybe open the door a bit longer to bring some other donors in. There are similar sort of techniques and practices across different industries. So, for example, airlines will have a history of overbooking passengers in order to maximize their sort of like how many seats are filled on the day. This very much sort of adopts the same similar practice, but rather than apply a blanket rate, allows us to be much more specific, which can have huge benefits. Not only are we just maximizing collection on the individual session, but it also allows us to get much more new donors through the door as well, as availability of appointments is such a common challenge we get from our donors. I think that's all I've got time for, but I will be around in the breakout rooms after as well if anyone does have any further questions. So thank you very much, everyone.
Brilliant. Thanks ever so much, Sam. That's looking fantastic. Another really interesting and potentially impactful project. Sarah, I believe we have next. So please, Sarah, join us and share your screen. Sam, you may have to stop sharing, or I might be able to stop it for you. There we go.
Thanks. Are you able to see that now?
Yep, that's coming through.
Okay, fab, thanks. Yeah, so my project is on modelling GP phone calls using discrete event simulation. And the project aim of this was to kind of build on process mining work around GP calls data that was already done by NHS England, and to use discrete event simulation to kind of build on this work. The original aim was to add in 111 calls as well and emergency department data, but inevitably I only had time to focus on the GP call stuff, but that's something that could be added in. And I guess kind of the reason for discrete event simulation was that it allows us to have that ability to test out how different scenarios would work. So if we change one part of the system, so for example, the number of GP receptionists, how does that impact another part of the system? So how long a patient waits for their call to be answered. And so this just briefly is showing kind of the mapping out of relevant pathways that was a kind of useful guide when I was actually coding the discrete event simulation. I'm not going to go into this too much. There's kind of two parts of this part is all around kind of patients that call the GP, and then we've also got to consider patients that turn up in person, because both of these are going to use receptionists as a kind of key resource that needs to be modelled. And so using this, I was able to produce an app similar to other people with Streamlit, and basically it means that we've got lots of parameters that the user can input and adjust. There's loads here, things around demand, things around activity times, the number of kind of the resources you have, so your receptionists, things around probabilities of repeated calls, so kind of how often are people calling back. And the app also has kind of 4 visualizations. So we have things around your mean queue time for calling the GP. We've got 2 kind of scenarios side by side here. We've also got a visualization on looking at the number of calls per caller. So are they calling back? And also the answer rate for the GP practice, and also the mean queue time for in-person patients as well. And then I very briefly got a quick demo of the web app, because live never works. So basically, yeah, you've got all of your parameters. If you run the simulation, you then get a table that summarizes all of those different parameters for that first scenario that you've run, and then you get to see these 4 visualizations just for that scenario. And then you could decide to change something. So increase the frequency that people are calling, add another GP receptionist, run it again, and you've now got scenario 1 and 2 kind of side by side. You can see how you've done kind of different parameter choices, and then you can see those visuals that I mentioned with your 2 scenarios. So that's a very quick taste of my project. Thank you.
Lovely work. Thanks very much, and really liking the work you've done on the scenario modelling. That's looking fantastic. Brilliant. So on to our next ones. So we now have Chris and Beth, I believe, talking to us about modelling HRG coding.
Thanks very much. So this is a progress update on some work that I have been doing with my colleague Chris Todd, and we've been looking at using classification modelling techniques to investigate changes in health resource group coding over time. So to give a bit of background on the project, an HRG code is used for payment by results. It's a code that is used to group together patient events that have similar expected resource use. And the code itself is derived from the procedure code and diagnosis codes on the patient's records. So to give an example here, this is for cataract extraction and lens implants. The HRG code is 5 characters. The first 4, the root, are related to the procedure. And then the code on the end there is the complexity code, and is based on additional diagnosis codes on the patient record. In the case of BZ34, there are 3 levels of complexity, and the complexity is decided by the codes on the patient's record that accrue points. So in this example here, I've got 2 patients, both with diabetic cataract. Our first patient has a number of additional diagnosis codes that accrue points, so puts him in the most complex bracket, whereas our second patient doesn't have the same number of additional codes, so is a lower complexity patient. An analyst colleague of ours had observed that over time, there seemed to be a shift in the proportion of the more complex cases. So he was interested to understand whether this was a real effect or due to what is called coding creep. Why is this a problem? Well, obviously, if you've got more complex cases, it's going to result in an increase in the expected cost. So the hypothesis was that the introduction of electronic patient records, which means that less relevant diagnosis codes might be included in the coding, has resulted in an increase in the apparent patient complexity. So this is where, rather than perhaps manually putting in additional diagnosis codes, the codes are taken directly from the patient records. Our approach has been to test and train predictive classification models for 2 different time periods. So pre-electronic patient records in 2016 and then in 2023. The diagnosis codes are the features used for classification. And then we can assess and compare model metrics with different data sets. So at the top here, we've got a confusion matrix for the model trained and tested with 2016 data, and then running it again with data from 2023. We're looking for those differences. We're also using explainable AI, including SHAP values, to understand feature importance. So really, we're at the end of the exploration phase. There were challenges around accessing data and the data platform and understanding the data in the codes. So now we're looking to understand what the SHAP values are telling us, and we'd be really interested to talk to anyone who might have clinical experience of HRG coding as well. Thank you.
Fantastic, thanks very much. And it's really lovely to see just the variety of applications of things like machine learning. I think it's a really powerful thing that comes through across the course of today, is just how many areas that these kinds of techniques can be applied in. So I'm sure you'll have lots of interest and people joining you in the breakout rooms. So we'll go on to our final presentation in this lightning talk session. So I will hand over to Rochelle.
Thank you. Let me share my screen. Can you all see that?
It's just starting to come through. Yeah, that's showing up now.
Okay. Hi everyone, I'm Rochelle, I'm a business analyst and I work for Epsom and St Helier University NHS Trust, and this is my HSMA journey. Welcome to Pressure Points, a year of modelling, also known as the modelling saga, because honestly, no one warned me that the plot twist would be simulating bed loss while running on coffee and occupancy charts. So this is a story of how I went from Hello World in Python to trying to answer where do beds go, but also using data to understand how care is delivered and what happens when pressure builds faster than capacity. So HSMA gave me a new toolbox, and each project focused on real operational challenges in the NHS, capacity, access, care delivery, and I'll briefly take you through those 3 projects. So one of my first projects I started looked at predicting gestational diabetes mellitus, or GDM, and used routinely collected data from Badgernet. So we trained a machine learning model to predict gestational diabetes early in pregnancy, which enabled us to start interventions way before definitive tests like the OGTT, which is the oral glucose tolerance test. And we use SHAP blocks to explain the output. So SHAP is shapely additive explanations, and is a way of giving every feature a chance to explain itself, even if you say BMI talks the loudest. But this model is still in development, but it's already showing promise, and it helps to spot risks earlier. The next project that I explored looked at travel, and that's if maternity care pathways were reconfigured using already available LSOA geolocation data extracted from postcodes of pregnant women who attended the trust in the past year, and routing APIs, or our trusty friend Google, to map out these routes. So essentially we assess travel times from patient areas to nearby hospitals. The results? In some areas, travel could increase significantly, and timing matters when you're in labour. And at the same time, directing patients to the nearest hospitals based on the shortest travel time, and could ease pressure on busy hospitals, helping to free up resources and maintain quality care without risking overcrowding. Now, this model simulates patient flow under different bed scenarios using actual admission and discharge data. It helps answer if we cut certain amount of beds, how much faster would we need to discharge patients? We found that if a small sustained length of stay cuts aren't always enough, so if you don't time them right, the system tips into overload. So this tool helps make the invisible risk visible. It becomes real. And the answer, significant and sustained reductions, not just short-term fixes. It's a powerful way to make the invisible pressures more visible. So every model has a shared clean pressure, whether it be patient volume, too few beds, or too many miles travelled. And each project showed that the data could help us see the pressure coming and maybe do something about it. And HSMA has given me the confidence not to just analyse what's happening, but model what might happen next. Thank you.
Fantastic, thank you. And it's brilliant to see that you've adopted so many of the techniques covered on the course. You know, huge, you know, hats off to you for picking up so many complex and quite different things. And also, you know, we do aim to give everyone a mild data obsession, as you mentioned on your slides. I'm glad we succeeded in that case. Brilliant work.